Here's some help with how to write the formula of an ionic compound that contains a polyatomic ion. The question says, write each ionic compound as a chemical formula. And the first one they have is barium nitrate. So what we're going to do with these is first write the ions that are combining separately, and then we'll combine them. So first, barium. Barium is sort of on the left side of the periodic table. Because it's in column 2A, it's going to have a +2 charge. So to write the barium ion, we'll write Ba, the symbol, and then the +2 in the top right. Now, nitrate, you'll notice, ends in ATE. The only names of compounds that do not end in "ide" have what are called polyatomic ions. So because you see that nitrate does not end in IDE, you know that nitrate must be a polyatomic ion. So a polyatomic ion is a group of atoms that all sticks together and as a big clump shares a charge. And these are lists of them, so you can see that these atoms are all clumping together, and all together they have the charge that's written at the top right. So this is one thing, one ion. And the name for these ions you would have to get either from memory or from a table. So in this case, we're looking for nitrate. That's here. And so nitrate is an NO3 -1 ion. So to write nitrate, we'll write NO3 -1. Now that we have the ions separately, we want to combine them, and so to do that, you crisscross the charges. So the 1 that's at the top of nitrate is going to go at the bottom of barium, and because it's a 1, you don't write it in. Just by writing the Ba, you know you have one of them. The 2 that's at the top right of barium is going to go on the bottom right of nitrate, the whole thing. So we want 2 nitrate ions. Now, we can't leave it like this, because as written, we would only have 1 nitrogen and 32 oxygens. Instead, we want 2 of that whole ion, so we put parentheses around the nitrate to show that we have 2 of that whole ion. And so that is the formula for barium nitrate. So if you were to take nitrogen and oxygen and put them together in just the right way, you'd get nitrate, and then combine that with barium, and you would get barium nitrate. Barium nitrate makes flames turn the color green, and so it's used in fireworks to create green fireworks. How about iron 2 hydroxide? What's the formula for that? So first, notice that iron is a transition metal, and so we're not going to get the charge from the column it's in on the periodic table. Rather, we're going to get it from the name. The Roman numeral after iron tells us the charge on iron. So we're going to have Fe 2+, because we have a Roman numeral of 2. And the Roman numerals are always a positive charge, so it'll always be whatever the number is and a plus sign, so iron 2+. Hydroxide is a famous polyatomic ion, so you would want to find out what that is, you'd want to go to a table of polyatomic ions, look for it. Here it's kind of toward the bottom, and hydroxide is OH with a -1 charge. So hydroxide is OH with a -1 charge. We'll just write that ion in. Now that we have the ions separately, we're going to crisscross the charges to find out what the compound is when they combine. So take the 1 that's at the top right of the hydroxide, that's going to go at the bottom right of iron, and because it's a 1, you don't write it in, so just Fe. Then take the 2 that's at the top right of iron and put that at the bottom right of the hydroxide, the OH. But again, as we have it written in, this would mean we only have 1 oxygen and 2 hydrogens, whereas what we really want are 2 hydroxides. So you'd put parentheses around that hydroxide. And so the formula for iron 2 hydroxide would be Fe, and parentheses OH and parentheses 2. So if you take hydrogen and oxygen and you mix them together in just the right way, you'll get hydroxide. And if you combine that with iron, you'll get iron 2 hydroxide. You can see that forming in this test tube here. And iron 2 hydroxide is sometimes used to take poisonous selenium ions, they're called selenites or selenites, out of wetlands. So those selenates or selenites are dissolved in wetland waters, and people are trying to use iron 2 hydroxide to take them out and clean the waters. So hydrogen, you'll notice here I have pictures of gas clouds in outer space. Hydrogen is the simplest element. It's just one proton with one electron going around it, and it's also the most abundant element in the universe. The gigantic gas clouds in outer space are made up of huge amounts of hydrogen. So here are some pictures of gas clouds that are just gigantic globs of hydrogen in outer space. These clouds of hydrogen are also where stars are born. Here's the silhouette. So this background, this dark part in the center is a gas cloud that's blocking the light from the stars behind it from coming through. Okay, sodium carbonate, what's the formula for that? First, let's write the ions separately. So sodium is in column 1A, so it has a +1 charge. So to write the sodium ion, we'll write Na and a +1 in the top right. Then to write out carbonate, one thing you should notice in the name is that it doesn't end in IDE. And if a name ever doesn't end in IDE, it means that you have a polyatomic ion. So we'll go to a table of polyatomic ions, look for carbonate. It's right there towards the top in this table. And so carbonate is CO3 with a 2- charge. So to write carbonate, we're just going to write CO3 with a 2- charge. And so now we have both of our ions separately. We're going to crisscross the charges to see the compound that they form. So the 2 at the top right of carbonate is going to go to the bottom right of sodium. Notice I'm not including the plus or minus sign, just the number. And the 1 that's at the top right of sodium is going to go on the bottom right of carbonate, but because it's a 1, you don't write it in. So the formula for sodium carbonate is Na2CO3. So if you take carbon and oxygen and mix them together in just the right way to get carbonate, and then combine that with sodium, you'll get sodium carbonate. Sodium carbonate has a bunch of uses. They add it to different breads to help them to brown. So on the left you have a Chinese mooncake, on the right you have a Bavarian pretzel, and it's sodium carbonate that's helping them get that dark brown color at the top. They also put them in powders to make them fizz, and in toothpaste to help it foam. And you can use sodium carbonate to get oil and wine stains out of clothes in the form of baking soda. And also sodium carbonate is added to pools to help regulate the pH. Okay, iron 3 phosphate, what's the formula for that? First, let's write the ions. Now, iron is a transition metal, so we're not going to get its charge from the periodic table. We're going to get it from the name. The Roman numeral tells us the charge on iron, so we'll write Fe for iron, and the Roman numerals are always a positive charge, so it's +3 for the charge in the top right corner. For phosphate, notice that it ends in ATE, not in IDE. If a name ever doesn't end in IDE, it means you have a polyatomic ion, and so you'd go to a table of polyatomic ions and look for phosphate. Here it's toward the bottom, and so phosphate is PO4 with a 3- charge. So we'll write that in, PO4 with a 3- charge. Now that we have the two ions, we'll see how they combine. Now, if the charges are ever the same, you can just rewrite the two elements together without the charges. The charges are what makes them stick together, and if they have the same charge, then one of each come together to cancel out the charges. So this +3 will combine with the -3 and give you 0 overall, so it'll stop being sticky when just one of each combines. So if the charges are ever the same, you don't have to crisscross them. You can just rewrite each of the ions without the charges next to each other. So iron 3 phosphate is FePO4. And so if you were to take phosphorus and oxygen and combine them in just the right way to get phosphate, and then react that with iron, you would get iron 3 phosphate. Iron 3 phosphate can be added to regular iron to help it stop rusting, to prevent it from rusting. So here this is a picture of the Iron Pillar of Delhi in Delhi, India, which was erected over 1,500 years ago. And even though it's made of iron and it's in a very humid climate, so normally iron rusts in the presence of a humid climate, even though that's the case, here it hasn't rusted for over 1,500 years. partly because the civilization that erected it added iron 3 phosphate to the iron, and that's preventing this iron from rusting. How about calcium carbonate? What's the formula for that? So first, let's write each ion separately. Calcium is in column 2A, so it has a +2 charge. So to write that ion, we have Ca with a 2+ in the top right corner. If you look at carbonate, you'll notice that it doesn't end in IDE, right? It ends in 8. So because it doesn't end in IDE, you know that it must be a polyatomic ion. So go to the table of polyatomic ions and look for carbonate, and there it is at the top. So carbonate is CO3 with a 2- charge. So to write that ion in, we'll write CO3 with a 2- charge. So these are our ions separately. Because each of these ions has the same type of charge, same amount of charge, 2+ here and 2- there, the charges are the same amount, you can rewrite each of the elements without the charges together, so CaCO3, and that's the compound. So the compound for the formula for calcium carbonate is CaCO3. Calcium carbonate, CaCO3, is a really exciting compound. It occurs a lot on Earth. Here, the waters in this area in Turkey are so full of calcium carbonate that it hardens out of the water. And calcium carbonate is a white color, so you can see all of the white steps here are calcium carbonate hardening out of the water. So this is in Turkey. That also happens in other places in the world. Here is a spring in Yellowstone Park that's very rich in calcium carbonate, and it's hardening out as that white stuff here. Calcium carbonate is also what makes up stalactites and stalagmites in caves. It's the white stuff in the White Cliffs of Dover in the United Kingdom. It is the hard stuff in corals. And Florida is the only place in the continental United States that has coral reefs. The coral reefs are in red here, and the blue is the ocean floor. And actually, the Keys were originally coral reefs that just got higher and higher, and as the ocean levels got lower over geologic time, they were raised as little plateaus, as land masses. So actually, most of the Florida peninsula is as high as it is because for tens of millions of years it was gigantic coral reefs that would live, they would die, get compacted, new corals would be built on top of them, and so over time where the corals got raised, and so most of the ground in Florida is just ancient coral reefs that have hardened into rock. You can see on the Windley Key Fossil Reef Geological Park in Islamorada Key, Florida, where they've dug into the ground, and so here there's the walls of the rock that this key is sitting on, and you can see in those walls the corals that were made of calcium carbonate that got smushed into the ground to create the raised ground above the water as the ocean receded, as the ocean level fell. Calcium carbonate also makes up shells and pearls and eggshells and chalk, and the medication that people will give if you have weak bones, if people need to build stronger bones, they'll give them tablets of calcium carbonate. Calcium carbonate is marble, so like the marble in a marble countertop, or the marble in sculptures is calcium carbonate. So it's a really neat molecule, CaCO3. So if you were to combine carbon with oxygen, and just the right way to get carbonate, and then combine that with calcium, you'd get calcium carbonate. All right, same idea. Copper 2 hydroxide. So first, copper. Copper is a transition metal, so we're not going to get its charge from the column it's in on the periodic table. Rather, we're going to get it from the Roman numeral. So to write the ion for copper, you'd write Cu, and then in the top right, it's a 2+. Remember, the Roman numerals are always positive charges. Hydroxide is a famous polyatomic ion. So here, it's toward the bottom of this table of polyatomic ions, and it's OH with a -1 charge. So to write hydroxide, we'd write OH -1. So these are the two ions that are combining in this compound. How do they combine? To find that out, we have to crisscross the charges. So the 1 at the top right of hydroxide is going to go at the bottom of copper. And remember, you don't write the 1s in. And the 2 at the top right of copper is going to go at the bottom of hydroxide. But As written, this only has one oxygen and two hydrogens. We want two of that whole thing. So we put parentheses around the hydroxide. So the formula for copper 2 hydroxide is Cu, open parentheses, OH, close parentheses, 2. So if you were to take hydrogen and combine it with oxygen to get hydroxide, and then combine it with copper, you would get copper 2 hydroxide. This occurs naturally as the mineral spertinite, and it's very beautiful, so it's used for glazes in ceramics. How about magnesium nitride? So first let's write the ions. First, magnesium is in column 2A, so it has a +2 charge. So to write the ion for magnesium, you write Mg with a 2+ charge in the top right. For nitrite, notice it doesn't end in IDE. That's always a sign that you have a polyatomic ion. So in this table of polyatomic ions, you'd look for nitrite, you'd see it's toward the bottom. It's NO2 with a -1 charge. So to write the nitrite ion, you'd write NO2 with a -1 charge. So those are our ions separately. How do they combine? To find that out, we'll crisscross the charges. So the one at the top right of nitrate will go to the bottom right of magnesium, and because it's a 1, you don't write it in. And the 2 at the top of magnesium will go at the bottom of nitrate. And because we want 2 of that whole ion, we have to put parentheses around the NO2. And that is the formula for magnesium nitrite. So if you take nitrogen and oxygen and combine them to get nitrite, and then react that with magnesium, you'll get magnesium nitrite. How about ammonium sulfate? Now ammonium is actually a polyatomic ion. So you'd go to this table, you'd see it at the top of that second table on the right. Ammonium is NH4 with a plus charge. So ammonium, NH4 with a plus charge. Sulfate doesn't end in IDE, and so it also is a polyatomic ion. So we'll go back to the table, look for sulfate. It's at the very bottom. It's SO4 2-, and so we'll write that in. So these are our two ions, ammonium on the left and sulfate on the right. To get the compound, we have to crisscross the charges. So the 2 at the top of sulfate is going to go at the bottom of ammonium. And because we want 2 of that whole thing, we have to put it in parentheses. The 1 at the top of ammonium is going to go at the bottom of sulfate. And because it's a 1, you don't write it, so it's just SO4. And so that is the formula for ammonium sulfate. So if you were to combine nitrogen and hydrogen together in just the right way, you'd get ammonium. And hydrogen, in addition to being the big gas clouds in outer space, is also the gas that's used in gas stoves. And then if you combine sulfur and oxygen in just the right way, you'll get sulfate. And then if you combine those two together, you'll get ammonium sulfate. And ammonium sulfate is used as a fertilizer. How about aluminum phosphate? So first let's write the ions. Aluminum is in group 3A, so it has a 3+ charge. So to write the ion for aluminum, we'll write Al with a 3+. Phosphate does not end in IDE, so it must be a polyatomic ion. So we'll go to this table, look for phosphate. There it is. It's PO4 with a 3- charge. So to write the phosphate ion, we'll write PO4 with a 3- charge. Because the numbers and the charges are the same here, 3+ and 3-, we'll just rewrite those elements without the charges. And that's our compound. So it's a 1-to-1 ratio. So aluminum phosphate is AlPO4. So if you were to take phosphorus, which is the red on the end of a match, and mix it with oxygen in just the right way, you'll get phosphate, and then react that with aluminum, which is used in air conditioning ducts, you'll get aluminum phosphate. Aluminum phosphate occurs naturally in a pure form as berlinite, the mineral, and if water starts sticking inside of it, 2 water molecules for every 1 aluminum phosphate, you get a different mineral called variscite. How about sodium chlorate? What's the formula for that? First, let's write the ion. Sodium is in group 1A, so it has a +1 charge. So to write the ion for sodium, you write Na with a +1 in the top right. Chlorate does not end in IDE. That's a sign that you have a polyatomic ion, so we'll go to the table of polyatomic ions and look for chlorate. There it is, kind of in the middle. It's ClO3 with a -1 charge. So to write chlorate, we'll write ClO3 with a -1 charge. So those are the ions separately. How do they combine? Because the amount of charge on each of these ions is the same, a 1 in the sodium and a 1 in the chlorine, we're just going to write each of the ions together without their charges. So NaClO3. And that is the formula for sodium chlorate. So if you were to take chlorine and oxygen and react them in just the right way to get chlorate, and then react that with sodium, you would get sodium chlorate. Sodium chlorate is used to bleach the pulp that goes to make paper products. So in a recycling factory, you might get a whole bunch of brown or multicolored papers, or also if you're making paper fresh, you might get like a brown or grayish colored bark. Mush it all together, you'd get a pulp that kind of looks like this in the center, and then you'd treat that with sodium chlorate, and you would get this white pulp that can be used to make white paper or paper products. So that's one thing sodium chlorate is used for. Also, if you notice here, this NaCl, if it were by itself, it would be table salt. So what happens with sodium chlorate is if you heat it up, the oxygen vaporizes away as pure oxygen, and you're just left with table salt. So this is a really nice way to store pure oxygen, like if you might want oxygen in an emergency. And actually, above every seat in an airplane, they have sodium chlorate. And in those oxygen masks that come down, where are they getting that oxygen from? There's sodium chlorate above it, and if they need to produce oxygen, they just heat it up. This oxygen vaporizes away. That's what would come down these masks and that you breathe in, and you'd just be left with table salt above that. Thanks so much for your attention.